Hi, this is Ideal Gas Law video number 3. So the last time we discussed about ideal gas law, we kind of uh, asserted that this is kind of the format of the ideal gas law. P1 times V1 over N1 times N1 times T1 is equal to P2 times V2 over N2 times T2. However, in books, again, this is not the format that is most preferred. And we will kind of explain why that is in this video. Okay? So again, what this means is if you have a state of a gas, if you have a gas with a certain pressure, volume, uh, number of particles, and temperature, it will be equal to the second state if you change things around. If the pressure has changed, volume has changed, number of particles has changed, and temperature has changed. As long as you do some calculations, they will be equal. Okay, so let's do that. So let's take, for example, P1. Let's say pressure 1. So you have a gas, and that gas has 2.5 atm of pressure. Okay, and then it has 5 liters of volume, and then let's say it has 0.51 number of moles, 0.51 moles of particles, and then the temperature is 300 Kelvin. Let me complete that. This is liters, this is in moles, this is in Kelvin. Okay, so the thing is, let me erase this part first. Okay, let me erase this part first, and let me just calculate what is this. If I multiply 2.5 times 5, and then I divide it with the multiplication, the product of 0.51 times 300, what will be the result? Well, you can do that if you have calculators, but the answer is it will be 0.08 approximately. Okay, now bear with me, there is a point at the end of this discussion, but the point is, again, if you have state number 1, so you have a pressure, you have volume, you have number of moles, you have temperature. If you do this calculation wherein you multiply P1 and V1 divided by N1 and T1, so the answer will be 0.08. Okay, now question, what if I changed the pressure? Let's say I increase the pressure from 2.5 atm, I change it to 8 atm. And what if I decrease the volume? I will decrease it to 1/10 of its volume, so 0.5 liters. And then what if I decrease the number of moles, which is 0.08? And the temperature now becomes 600 Kelvin. So this is now P2, V2, N2, and T2. So let's change this. This is now P2, V2, N2, and T2. And then again, I do the calculation. So I have 8 times 0.5. I get the product of that. And then 0.08 times 600. And then I divide the P2 times V2 divided by N2 times T2. I will get an answer. And that answer, surprisingly, is also 0.08. Okay? Now, what if I change once again the variable such that now the pressure becomes 55 atm, the volume becomes 120 liters, it's a bigger volume this time, but I increase the temperature to 715 Kelvin, and then I again increase the number of moles into 112 moles. This is, by the way, in moles. And again, now this is now this is now situation number 3. So this is now pressure 3, volume 3, number of particles 3, and temperature 3. Okay, again, I'm very straightforward. I can just simply calculate 55 times 120 divided by 112 divided by 715, and guess what? The answer is 0.08. Okay, and so what do you notice here? What you notice is it seems that no matter how I change the values, when I calculate this, it seems to be a constant number. Okay, so whatever the values that I have for volume, pressure, number of particles, and temperature, as long as I do the calculation like this, where I multiply P times V divided by N over T, it will always end up with the same number, which is 0.08. So therefore, we say that it's a constant. So we say now that it doesn't matter if it's P1 or P2 or P3 or P4, as long as it's P multiplied by the V divided by the N and T, the answer will always be a constant. Okay? And this constant seems to be 0.08, right? So scientists noticed this pattern and they said, okay, let's invent then a constant. We call this a gas constant. Okay? So the ideal gas law states that if you take the pressure, multiply it with its volume, divide it with the product of the number of particles and the temperature of the gas, you will end up with the same number, and that number is R, or the gas constant. And this is a true constant. A true constant means it is doesn't change. So it's a true constant. And obviously that was just a rough calculation, but when scientists investigated this further, they found out that it is really true, that there is really a constant number, and that number is 0.0821. Obviously in our calculation we just stopped at 0.08, but this time it's 0.0821, or even in some other books it's actually 0.0805, but in our case we'll just round it off to 3 significant figures. So 0.0821, and this is now the gas constant. Okay, that's the gas constant. Now, if we analyze, how did we get this number? Well, we multiplied P and V divided with N and T. Okay, so let's analyze. Okay, what is P? Well, P was ATM, right? Atmosphere. What unit did we use for volume? Well, we used liters. How about the number of moles? Well, it's moles. How about the temperature? It's Kelvin. Okay, so therefore you have this constant, and this constant is 0.0821 atm liter per mole dot Kelvin. Okay, and again, that's because we are multiplying P times V divided by N times T. P is the atm, right? The atmosphere. V is the liters. N is the number of moles. And T is the temperature, which is in Kelvin. Okay, so that is a constant, and you have to memorize this. This is the gas constant. It's equivalent to 0.0821 atm liter mole dot Kelvin. So now we can now say that whatever the pressure is, whatever the volume is of an ideal gas, whatever is its number of particles and its temperature, it will always be equal to R. Okay, so this is now the preferred ideal gas law formulation in books. So instead of what I introduced to you, which is P1 V1 over N1 T1 is equal to P2 V2 over N2 T2, this is the ideal, this is what is preferred. But if you really think about it, they're the same, because you're just saying this state is equal to that state. So if they're equal, that means it must be a constant. Otherwise, why would they be equal? So therefore, you don't need to label this as 1 or 2 or 3 or 4, because any configuration of the 4 will always give you that constant, which is R. So the only thing that you have to remember here is that this formulation is actually, if you really think about it conceptually, it's just the same as that. It's just that here we are specifying two kind of configurations when you have a setup 1 and versus setup 2. In this case, you are saying, nope, this is a general statement for all setups. As long as you know the P, the V, and the N, and the T, when you do that calculation, you will always get the value, which is R, which is 0.0821 atm liter per mole dot Kelvin. Okay, so that's the idea for the gas law. So P times V divided by N times T is equal to the R, and that R will have a fixed value of 0.0821 atm liter per mole dot Kelvin. Now, because we are using pressure and volume, pressure instead of atm could also be in pascals, and volume here instead of liters could also be in meter cube. So if that's the case, then this whole thing changes. And the R will be equivalent to 8.314, and then this will be joule per mole Kelvin. This is only if you are using pascals, meter cube, mole, and then Kelvin. If you are using ATM, liter, mole, and Kelvin, then obviously this is the value. But in books, usually what is remembered is this one, and then this one is just kind of like a second option. If you are using pascals, meter cube, mole, and Kelvin, you use 8.314. But if you're using ATM, liter, mole, and Kelvin, you use 0.0821 ATM, liter, mole, Kelvin.